most of you got the answer correct. It's the normal degradation. There's no such thing that occurs in adipose tissue, and is really not necessarily reflected by the insulin. The most important issue is that, in fact, the other four are absolutely correct. Go to the next slide. So in terms of insulin, it has a biological effect, or not only on insulin stimulated glucose, but it also is an impairment in terms of liver, of fat, and of protein. And I think something we forget all the time. Insulin is a wide level of activity. We just happen to be measuring glucose, and that's why we think of it as glucocentric. But it is in fact affecting everything else. So when you look at insulin resistance, and this is a study where you looked at individuals, controls, type 2 diabetes, impaired glucose tolerance, obesity, or essential hypertension, and what you were doing was you were doing a hyperinsulinemic glucose clamp, giving a lot of exogenous insulin and finding out how much glucose there was required to stop hypoglycemia. And you can see here that in fact the people without diabetes had required twice as much glucose as the people with diabetes. Obviously, because these people were insulin insensitive, they required less for the same amount of insulin sent in. Impaired glucose tolerance behaved like type 2 diabetes. Obesity without abnormality in glucose behaved like type 2 diabetes. Essential hypertension behaved like type 2 diabetes. Insulin resistance can occur without an abnormality of glucose. It needs a beta cell to fail. So, insulin resistance at target tissue is differentially, meaning the liver is the most sensitive, then it's fat, and then muscle? Or is it in fact muscle is the most sensitive, liver, and then fat? Is it fat, liver, and muscle? Is it fat, muscle, and liver? Or is it equal at all three tissues? If you could put in your answer, please. Okay, so this is interesting. Basically, everyone said muscle was the most sensitive, liver was second most sensitive, and fat was the most resistant. In fact, it's the exact opposite. Think about it. You want to protect the organism. Therefore, if you are going to be able to protect the organism, every time you get some nutrition, you want to put something away into stores so you can survive the future. So fat is actually the most sensitive of those three tissues, then it's liver, and then it's muscle. And when you look at it in terms of insulin action, the finest thing insulin does at fat is to inhibit lipolysis. To inhibit 50% lipolysis, you need about 8 microunits of insulin. The finest thing insulin does at liver is to stop hepatic glucose output. To stop 50% hepatic glucose output, you need about 40 microunits of insulin. The finest thing insulin does at muscle is to cause glucose disposal into muscle. To have 50% glucose disposal, you need 200 microunits of insulin. So clearly, fat is the most sensitive, muscle is the most resistant. That is the resting muscle. The exercising muscle doesn't count, but the resting muscle. And it's very important to understand this, and it explains why every time you use an agent that basically either causes the release of insulin or alternatively is insulin itself, you will find that there is a tendency to weight gain. Because in spite of not getting absolute control, the fat is very sensitive to insulin. When you look at action of insulin at the liver, what you basically see is that the finest thing insulin does at the liver is to inhibit lipolysis. So a little bit of insulin stops ketosis. But then after that, you start to see inhibited gluconeogenesis, inhibited glycogenolysis, inhibited glucogenesis, and it's when all of these are done that you see an inhibition of hepatic glucose output. And this is related to the level of insulin. Notice that when you get inhibition of hepatic glucose output, you still haven't even started significant muscle glucose disposal. And so clearly insulin action is dependent on how much insulin you've got, even in an insulin-sensitive individual. Free fatty acids play a very major role in the development of the persistence of insulin resistance. When you have increased free fatty acids, your cell is saying, okay, I don't have my primary fuel glucose, I'm going to use my secondary fuel, free fatty acids. But because I want to protect glucose for the central nervous system, I'm not going to allow the cell to use glucose. So when you use free fatty acids as your fuel, basically what happens is that it stops glucose, it basically inhibits glucose utilization and contributes to hyperglycemia because you want to protect it. The question is, in normal it's not a problem, but once you get diabetes, it becomes a huge problem. This is what happens when you infuse free fatty acids into individuals who do not have diabetes. What you see here is basically glucose uptake is, with fat is markedly diminished. With fat, glycogen synthase is markedly diminished. Glycogenolysis is diminished. Glucose oxidation is diminished. You're not using glucose. You're using the free fatty acids. Non-oxidative glycolysis is about the same, and hepatic glucose output is clearly increased. Fat induces or worsens insulin resistance. So, what is the pathophysiology of diminished insulin secretion? You get genes, you get lifestyle and diet, insulin resistance. If you get a normal beta cell, all you get is hyperinsulinemia, normal glycemia. If you have an abnormal beta cell, it goes on to give you relative insulin deficiency and the development of hyperglycemia and type 2 diabetes. So it is the beta cell that finally becomes a problem. So what do we know about the beta cell? What we know about the beta cell is we know that we make it at 6 weeks of gestation. From the 6th week of gestation to the 12th week of gestation, the beta cell has only one job: propagate, become more. At the 12th week of gestation, when there's a placenta in place, the fetus now becomes a parasite. Sorry, that's not the way you think about babies, but the fact is that it is dependent on the host for nutrition, but it is independent of the host once it's got nutrition to deal with it. And that's where the beta cell comes in. So if you're going to give it too much food at the time of intrauterine environment, the beta cell has two jobs. One, produce insulin. Two, continue to propagate. If it's asked to work harder, it's not going to propagate. Do I have proof for this? If I take an embryo from a father rat and a mother rat that has no diabetes, that has no potential for genetic predisposition to diabetes, put into a rat that has no genetic predisposition to diabetes, but I give it diabetes by giving it streptozotocin, and I look at the beta cell mass in the fetus, in the newborn, it's 30% lower. Just the mere fact that the intrauterine environment was clearly elevated, you saw the effect in fetal beta cells. So it's clear that it starts in the uterus. Do we see it in humans? Some epidemiologic studies in the Pima Indians, when you looked at Pima Indians and you looked at the offspring, and you divided the offspring into people who did not have diabetes, none of the offspring had diabetes, and you divided their parents into having diabetes over the age of 55, between the age of 35 and 55, and having diabetes below the age of 35. If those individuals where the parents got diabetes over 55, in these absolutely normal offspring, they had already lost their first phase of insulin, 35% had already lost their first phase of insulin secretion. Compare this to those individuals whose parents had diabetes below 35, where 66% had already lost their first phase of insulin secretion. It is clearly an intrauterine predisposition. So, the earliest marker of beta cell dysfunction is a fasting blood sugar over 126, a hemoglobin A1C of over 6.5, loss of the first phase of insulin secretion as